All right. Any questions before we start? Have you completed exercise 1 by now?
Yes.
So, yeah.
Just a small doubt. In the exercise 1 third bit, I'm able to configure the DNS via the address, but it is not coming via the name, like q.org is not coming.
No?
It's not coming.
So how have you debugged that?
I didn't.
How have you say it's not coming? What do you mean it's not coming?
Like I'm not able to access the web browser using the.
So what have you done?
I tried to do it by static instead of doing via DHCP, but still it was not able to access. Like I gave the DNS server IP address over there in each and every PC, but it was still not coming.
Okay, I'm not really understanding what you did, but let me, the way I interpret you said, on the DNS server, you fill in the table or the information about IP and name. Right. So you have, the DNS server has the mapping between a certain string and an IP number, right? Okay. Great. If you are on the DNS server, can you resolve the IP address? Can you, on the DNS server, type ping a.org? And perhaps it's not able to ping it, but it goes, if you see a.org, and then you see this translates into an IP number. Do you see that? Okay. Have you started the DNS server?
Yes.
Did it start correctly? Or did it say, you made a mistake in my configuration?
It didn't say anything like that.
Where would you see that?
In the command prompt where I used the web browser in the desktop and tried to access it using the IP address. Then I got the page. But when I'm using the...
Nah, but the mapping is missing. Which web browser are you referring to? On which device?
Inside the Cisco packet tracer itself, in the desktop part, you have a web browser.
In which platform?
Actually, yes, there's a particular platform there where you can actually fill in. You can say www.q.org or ping as well. You can ping the IP address. Yeah. Or
I am aware of that. I'm trying to figure out on what device are you running this.
Okay.
On what device are you running that?
Okay, I'm on a host device.
On a host device. Okay. So on your host device, are you capable of talking to the DNS server?
Yes. I'm able to ping it.
You're able to ping it?
Yes.
Okay, good. Have you made any configurations to the host to adjust for the fact that you have a DNS server? You have, we're going to tie into this then nicely. You have, when you configure a device, you need to configure IP, You need to convert your, in my world, IP also includes mask. That's the absolute bare minimum. You need IP and mask. Stage 2, if you're kind of feeling you want to do more than just talk to your local network, you need a default route, or you need a router. Ideally, you need a default route, but it's sufficient to have a router that you know, okay, if I want to talk to this network, I'm going to go there. Default route is much better because then everything you don't know goes there. Now, if we take the next step, we don't want to talk IP numbers because we're humans, right? In the next step, we have to tell the computer, hey, if you get a DNS entry or a DNS name, who are you supposed to be talking to translate this string into an IP number? You need to provide the resolver address. Did you do that? Sometimes it's called resolver, sometimes it's called DNS server. Have you done that? No. So in that case, your computer sits there, gets a name, and then it only has its own local cache, DNS cache to check, and it's very unlikely that it will find a match. And then it will say, I don't know. Unable to resolve or something you should get. You get that?
Yes.
So unable to resolve means I cannot translate this. And then that should trigger you, hey, why can't you resolve this? I've set up a DNS server. Why don't you know the DNS server is over there? Ah, okay. Configuration, resolver, DNS server, not specified, IP number of DNS server. And then try. But you should also be able to resolve this locally on the DNS server. Yeah, for the host, you need to do that. But to ensure that the DNS actually works, because God knows things are going to be messed up in the DNS config, make sure that it works on the DNS server as well. More questions? If so, raise your hand while we talk. So, the outline for today is ARP and RARP, DHCP, boot BP. Then we're going to talk about DNS, but on the higher level of scale. But that includes this particular case that you mentioned too. And then we're going to talk about load balancing and the difference of resilience and redundancy, and the benefits of having load balancers to cope with both. So ARP and RARP. We encountered ARP in our previous lecture, IP Basics, remember? Address Resolution Protocol. This is when we translate from a layer 2 address to a layer 3. So basically, it works like we're on layer 3 and we need to know what is the layer 2 address of another layer 3 entity. So we send, hey, who has this IP address? Please tell, and then we put our layer 2 address. This is broadcasted out on the LAN segment. Pay attention, it's broadcasted out. If there's anybody who's listening and notices, hey, they're asking me for an address that I'm catering from, they're going to reply, hey, IP number X is available, and then they put the MAC address or layer 2 address that they have on the interface where they received the request. That goes as a unicast back to the destination. And the destination then can update their cache entry saying, hey, IP number, MAC address, interface, updated at this point in time. All right? Now, there are two versions of ARP that you should be aware of. That's proxy ARP or promiscuous ARP or the RPAC. This is when someone else answers on the behalf of the intended, the recipient, so to say. So for instance, I know that you are on that interface of me. I receive a request, ARP request here. I don't see it on this interface, but I know that that device is over there. So I take that and I can reply, hey, you can reach this entity through this address. Then when there's a packet coming for that address or frame, I have to receive it and I need to forward it accordingly. But the key word is someone else answers. This causes a little bit of a problem. It's good in this scenario, but it has some drawbacks as well. Can you think about a case where it might have a drawback?
It can lead to a man in the middle.
Anybody knows what a man in the middle is?
Yes.
How many does not know what a man in the middle is? Okay, so man in the middle is a security hack, or not a concept, because it's a, but you usually hear it in a security context. A man in the middle is when your traffic or communication is relayed through a third party and the communicating entities are not aware about this entity in between. So in this case, you usually hear about Alice and Bob, or Alice, Bob, and Charlie. I kind of prefer Alice, Bob, and Charlie. So for instance, and here's perhaps an issue of the ARP protocol. If I say, where's Khan? And Khan answers, I get his address, I can send a message. But now if you also say, I'm Khan, I get 2 replies to my request. And now, the way that ARP has been implemented, I'm going to be a little bit confused. Or actually, I'm not really confused, because whenever I get a reply, I insert that information, IP, MAC number. So if Khan replies first, bam, I will probably send my message straight away. But slightly after, I get his reply, and now I replace the valid entry with his MAC number. And suddenly, when I'm talking to Khan, I'm sending it to him. So. But it has its benefit, it has its uses. Gracious ARP. Gracious ARP is used, for instance, I think it's used by DHCP. When you have been assigned an IP address, or when you have an IP address, you send a gracious ARP saying, I got the IP address of A. You send a message, hey, who has A? Please tell A. And then you say, it includes like a true address, to address of the guy who sends this. Now, if there is someone else listening on that address, they're supposed to reply. And then we get a notification, hey, I'm A, but there's someone else also claiming to be A. This will not work out fine, right? Because if there's a packet destined for A, we will just have this issue that we described. Is he getting it or Khan getting it? we can also use gracious ARP to update the ARP caches. And now this could also be an issue, right? We know that Khan is over there, but suddenly has, hey, I'm Khan, this is my address. We don't even have to worry about proxy ARP. Gracious ARP can do that, inject the man in the middle for us. Oh, but, okay, so there is a case. In the case where you have two routers or two entities that is sharing an IP. So the case, this case shows it. This is the normal operations excluding the fire. When these guys are running, they talk to default gateway 001. That goes to one of them. When the Bead notice that A is having problems, they send an up GARP. Hey, 01 is now handled by this address. And then they switch the traffic over to B. And vice versa. So it has a use case in this scenario. So it we can push out updates without having these guys to send an ARP and then be rejected or not having a reply to it. So it has a valid use case. Should perhaps just include some additional security, because there's nothing that prevents either of these guys saying, hey, I am 001. So RARP, Reverse Address Resolution Protocol. As it said, it's similar to ARP, but it's in the opposite. Instead of trying to match layer 3 to layer 2, we're trying to match layer 2 to layer 3. It has been used by a protocol that predates boot DHCP called BootP. But BootP has been having a dwindling environment. There's less users of it, but it's still around. The request, as I said, it's broadcast just like the ARP. Reply is unicast, just like ARP. The difference is that this requires you to set up a RARP server on your network, compared to ARP, which is natively included in your IP stack. So it requires additional infrastructure in your network. And this is for matching layer 2 to layer 3. I have never used RARP, but I have had the desire to identify layer 3 addresses based on layer 2 addresses. Now usually you can just watch traffic and eventually you will see that there's a packet, and then you can match layer 2 to layer 3 based on that. But I never really used a dedicated RARP server for that. And this brings us to DHCP. So we're going to talk, we have two protocols here that we're going to talk about. We're going to talk about the bootstrap protocol, BootP, and the DHCP, Dynamic Host Configuration Protocol. The goal of both protocols are to configure the network of a device. And first and primarily, as I said when we had our chat, the first and primary objective is to push out IP and mask, default route or default gateway, then DNS server, and then if you have additional routes or anything that you would like to push out. And the reason for DHCP and Dynamic and BootP is because when you have a network that is growing beyond a couple of devices, you're kind of not being able to manage this on your own as a human. So you need to have some kind of procedure or system that does this. Now, we can do that statically, having a file where we track when a new device is added, we grab the next available IP number and we hard code that to the device. That's absolutely plausible. The drawback with that is that you lose dynamics. So, for instance, that you need to change your network or your router is going to die or is being replaced. So instead of having default route .1, for instance, there's no requirement or mandate that states that the router needs to be placed on the first IP address of a network. You can place it anywhere within the network that is available. The only two exclusions are the network address and the broadcast address. Within that span, you can place it wherever you want it. Personally, I usually put it at .1 because that's easy to remember. But there's this thing called security through obscurity. So it might be beneficial to not have it there, because if it's on a well-known location, people that gain access to your network can also then access your router to get out. But never mind that. So by having something that can dynamically change, we can save time and we can reduce errors. If I'm tasking two network engineers to set up a numbering plan or assign, hey, here's a new device, put this into the network, and it's a static assignment, unless you know what addresses have been assigned, they will just pick something, and the probability of this being something that is already used is non-zero. That can also cause all types of trouble. So the way I see it, dynamic host configuration is the way to do it. Because that is one thing that can track this information for you. It assigns it, it revokes it, it tracks when was it requested, etc., etc. And you can also push out information through this request or in the reply to the request. As the slide says, BootP came first, then DHCP. I'm not really sure when BootP came about, but I'm thinking 80s, DHCP late 80s or something like this. So they have been around for some time. So for that reason, I'm not going to talk too much about BootP. They are principally the same. BootP has just a few, has less options compared to DHCP. BootP is basically just IP mask and default route, possibly and DNS. That's it. Whereas DHCP can push out a lot more information. And actually has a way of pushing out arbitrary information. So the communication model looks as follows. You have to have a server that is ready and available and listening for requests. The server listens on UDP port, and I always get this wrong. I'm not sure if it's 68 or 67. I think 68, I think. Which is it?
16.
16.
68.
68. Not really important, but it's supposed to be on a well-known port. The client sends a broadcast because it doesn't know the IP address of the server, right? So it says, hey, I want to discover a DHCP server, or I want to discover. So it sends a broadcast, which would be, at this point, it doesn't really know what network is it on, right? Because if it knows its network, it could at least send on the network address, but it doesn't know that. So it sends a message on 000, quad zeros, or equivalent of IPv6. UDP port 68. Message is discover. Now, this is then received by all of the devices on the network because it's a broadcast. Luckily, or hopefully, there will only be one DHCP server listening on that particular port. There could be multiples. But the server receives that request and then pushes out an offer. Hey, I'm offering you this IP number, this mask, this DNS, this route, these routes, etc., etc. And that is pushed directly to the client, to the MAC address. The client receives this, and if it likes it, because, hey, it might have received multiple offers from different DNS servers, DHCP servers. If it likes it, it will then send a request. Hey, can I get this IP number, etc., etc., etc.? Because there might be some timing issues how far things have gone. If it's okay, because it should be the server, hey, you want this address? So can I have that address? Right? The server then acknowledges it, and at that point in time, the lease is confirmed. And a lease is the duration of time when an IP address is assigned to that client. I'm just going to take a peek ahead now. The lease time is configured on the server. This could be from a few seconds to several days or weeks. The packet that is used, I hope you understand that it has an IP header followed by the UDP, port 67 or 68, and then the DHCP message. This is just broadcast. Okay. Oh, so I had it right. Both 67 and 68 are used. So this is how the message looks. The IP header has source quad 8. The destination is quad F 255.255.255. The protocol is 17 because that's the number of UDP in IP language. The UDP has source 68 and destination 67. We have an operational code, an H type, H length, and number of hops. There's a transaction ID, the number of seconds, which I can't remember what that is, and then the flags. Client IP, in the case that the client has an IP, I think this is where they can put it. If I already have an address, I can put it there. I have this. So, this is how it looks. Here is a client. This is, by the way, snipped from Wireshark. If you don't know Wireshark, look it up and use it. So, what we're seeing that we have 366 bytes on the wire. That's layer 2 size. It is an Ethernet 2 frame. The source is the source address is the source MAC number. And we see that it's actually decoded. Remember what we talked about organizational OIDs? So this is the MAC address. And we see that the first part here, 36D7 and 2E, actually, those are part of the Dell range. And then 0389. Destination is broadcast to FFFs, IP version 4, source, destination, UDP, source port 68, destination 67. This is a bootstrap protocol request. It's decoded as bootstrap, but it's DHCP because there's more stuff around it. So, message type, boot request, type 1, hardware type 01 Ethernet. The length of the hardware address is 6 bytes. The number of hops that this has been passed through is 0. Transaction ID is just something that the client randomly picks, as far as I remember, just to make sure that it's not mixing requests and responses. Boot flags, 8,000, and then it doesn't really have any information, so these are zeros. But it prepares the message that the server will use to reply. The MAC address that the device has, and in the case that there's, in order to handle different layer 2 technologies and layer 2 sizes, we need to have occasionally padding to make sure that we're finding ourselves somewhere where it makes sense in the message. Because there's a finite amount of space for that, but so sometimes we need to pad. Then there are a bunch of options in this message. So the message 53 indicates that it's a DHCP message. So if this information would not have been present, that would have just been a classical boot P message. As this is present, magic cookies DHCP, we know, okay, could potentially be additional information here. So what the client wants to have, it wants to have a client identifier. It wants to have a requested IP address. We want to know the DHCP server identifier. We want to know our host name. We want to know our fully qualified name. That is the full DNS name. Vendor class identifier. This is something that is included from the client. And then 255 means there's nothing more. So this is what's being pushed on the wire to the unknown, unaware DHCP server. So the thing that here is the reply. It is the same thing, same message, but just 3 changes. Of course, the layer 2 information has changed. This goes again to a broadcast from the source of the DHCP server. Again, here we see it's Intel Core something. It's an IP version 4 protocol, and now the source address is the one that is used by the DHCP server. Destination is still 255. We did not put the broadcast address, the unicast address here. So this is still a broadcast. Everybody gonna see this. And then this is reply. And then here we put the information. Your address is going to be 10.30.40. Next server IP address is, bad example, 10.1.03. Here should be a mask somewhere as well. It's going to be there. It's not just shown. So we got that. The client gets this. I think I made a copy-paste error here, because that's the same frame. Here we should have put additional information in to say, okay, I'm going to get this right. And in this one here, this is again copy fail. Here we should have, this should have been, it says acknowledgement there. Okay, so this is the request. I'm looking at the frame number here, frame 975. The offer is 974. We get the offer before we send the request. This is something fishy going on here. Request 75, okay, that's the same as this thing. And here's the acknowledgement, 976. So kind of, the offer should have been that's the request. This should have been a discover. Okay. But you see, the point that I'm trying, you should read the book. Should read the book about it. The point that it's a 4-stage process: a request, an offer, an discover, offer, request, acknowledge. These are the stages to remember. It's not, hey, give me an IP number. Hey, John, go. That would be boot P. DHCP has 4. Offer, discover, offer, request, acknowledge. Once you have acknowledged, we're going to go into a different procedure. The stuff that we can do with DHCP is we can push out time servers, for instance. And time servers are NTP. Anybody heard about NTP? It's a way of synchronizing times on multiple devices. That is super critical when you are in the state of, or in the context of correlating events on different locations. It's very difficult to debug something that says, well, let's take this for example. We got the offer before we sent the request. Now if you have that in time, well, I sent you that letter at 10:50, but I got it at 10:40, right? So timing is critical, and it's good to have a good time source. And it's perhaps sufficient sometimes to have the same time source for a group of devices, because you know, okay, those devices, they are belonging to that watch, those devices belong to that watch. There inside of those devices we can correlate them very simply. Within those we can correlate, but the moment we need to correlate in between them, then we need to compare what are the differences in the watches, adjust for that, and then we can correlate between them. But we can push out time servers. We can push out DNS and name servers. So who's going to handle our lookups? That device, wherever. Log servers. So instead of logging the information locally to the computer, we push it to one log server where we have everything. That is really handy because you can just go blah 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 var log, host name, entity service. Okay, I have a problem. Okay, and then you can go and check it out. Instead of SSH to that particular computer, look it up. Okay, that is the issue, and then fix it. Sometimes it's just an intermittent problem, and you don't really need to fix it, just need to be aware of it. You can push out host name, of course, just as it's easier to remember a host name compared to an IP number. And us humans prefer to type strings compared to just numbers, which are strings too. Domain name, just the extended version of the host name where it doesn't belong. MTU, maximum transfer unit. That is how big is a device allowed to push packets onto the network. This is normally limited by the underlying layer 2 technology. So in Ethernet, that will usually be 1500 bytes. But in the case that, you know, these devices that are on this network, they will be coming to our gateway or router, and then it will be pushed onto a VPN tunnel. That VPN tunnel takes an IP packet, puts on an additional IP header, an additional transport header. The IP header is 20 bytes, the transport header is another 20 bytes, that becomes 40 bytes, and suddenly if we have already a packet that is 1500 bytes, shoving on an additional 40 bytes will make it 1540 bytes, and we will not be able to push that onto a standard Ethernet. Then we need to do fragmentation, and fragmentation takes time and makes life difficult. We can do it, but it consumes time and resources. So it is better to just to tell all the devices, hey, your MTU is 1400 bytes. So they will then be generating 1400 bytes packets. We get them, 1400 bytes, we junk that in our payload, strap on the headers, and still we have a couple of 60 bytes left, and we can ship it off. All right? So MTU is one of these things. However, you should be cautious with MTU because you might have other things to consider as well. For instance, as I said, in jumbo Ethernet, gigabit Ethernet, you can do jumbo frames, 9,000 bytes. That's fine, that makes the communication more efficient, but in the case that you happen to traverse something, a link that is not jumbo capable, everything will go bad. Or you're talking to a device that is not jumbo capable or has not configured jumbo frames, things will become really complicated. So you have to pay attention when you're using MTU or modifying MTU. Standard is good normally, but sometimes you need to scale it down, and scaling it down is usually not a problem. Making it bigger than the standard 1500 bytes to accommodate for jumbo frames could be an issue. Routes. We can push out routes through DNS, DHCP. So for instance, the classical case is we have our default route. this handles everything. But then we set up an additional router that handles a certain segment of our network. So instead of pushing everything up to our default route and that pushing it over to the next destination, we say, okay, if you're going to the servers, for instance, use this route. Go here instead. If you're going to the internet and surfing, use this path. So by pushing out routes this way, we can push that information down to the hosts. So they can do a smart selection on their exit strategy, so to say. So, the DHCP state machine. So this is how the state machine looks. It is a 6-state machine. It starts up here when the host boots. So it initializes, and when it initializes it, it usually reads a config or something. And in this config file you specify when you do DHCP, these are the things you should request, these are the things you require, and these are the things you don't care or you don't want. I'm basing this on my experience from Linux devices. This is how, as far as I remember, the ICS DHCP client works. So it sends DHCP discover, comes here. The server selects an address and makes an offer, and it keeps on there as long as it gets a DHCP discover message. So if it gets it once, it will do an offer. If it doesn't get a request for that offer, after a amount of time, it will resend that request offer again, assuming that the offer was lost or destroyed, because it's connectionless protocol, so we don't know, anything can be lost at any time. So it resides there, but eventually, not included in this one, there is a fallback that drops it out, but it's not included in this one because it's not going to be, if someone asks for an address and never acknowledges that, if you do that, your server will keep on sending this offer, and eventually you will just be sending offers, not doing anything else. So if it gets the request, the client got the offer and now made the request, it comes down to the request, and then the server sends the acknowledgement. At that point in time, the client is bound to that address. So this is what we talked about in the discover, offer, request, acknowledgement, right? The 4 stages. The client now is bound. So it has an IP address and this information. That includes a lease time. This is how long are you allowed to have this address. When 50% of that time has expired, we have to make a choice. We send a request again. We can always do a leave, but we send our request again. Hey, I got this IP number. Can I keep it? Comes up here, and the server says, yeah, there's no problem. This becomes a renew. You go back here. Now you have the lease for another lease time. So if your lease time was 1 hour, after 30 minutes you will send, hey, can I have this for another hour? You drop down here, and then you will have it for another hour. Again, after 30 minutes, you will redo this. So then you move to the renew state. If that is acknowledged, you can drop here. If it's not approved, you keep on sending this renew request until half of that time has elapsed again. Another 25%. You send the request again to the server, and if the server at that point in time grants the request, it's rebound, you rebind it, and then you get an acknowledgement that you drop down here. If you don't get acknowledged, or you possibly get a negative acknowledge, you can keep your time all the way up to release time expires. At that point in time, you need to do a release, which brings you up here. Or if you're in this stage, you drop it up here. And then you go back to the initialization phase. Hey, please, I'm discovering an IP address. And then you go back to the normal phase. So this is the phases of the client. So you have initialized, select request, bound, renew. These are the predominant ones. Normally, you go through this once, and then you're being cycled around these guys. But the point to remember here is that during the lease time, the client has the IP address. If you want to make the client change address, you cannot push that onto the client. The client needs to release it and then re-request, and then it can obtain another address. So with that in mind, we are going to have a balancing act here. How big should our lease times be? If we set a large lease time, we will not have a lot of requests. They will happen periodically, but only perhaps once in a while. Let's say we have a lease time of 24 hours. So after 24 hours, every 12 hours we will get a bunch of requests, renewals. But it will take, in the case that we need to make it fundamental change, it will take us maximum 24 hours before everybody has re-requested an address. Properly re-requested. If we have a smaller time, let's say an hour, we're going to have this every 30 minutes. But then it will just take us 1 hour to implement a change, right? So there are benefits and drawbacks with all of those approaches. Just because you change that DHCP config on the server does not mean that the client will change directly. Have that in mind. Domain name system. Any questions of boot, P, RARP, and DNS, DHCP? No? Okay. So, The aim of DNS is to simplify the translations of strings to layer 3 addresses. For instance, www.bdh.se, google.com, or r.sn-5go7yn7e.c doc-000-sj google user content.com. All of those are examples of DNS names. Sometimes the names are indications of where that information is. I think that stands for San Jose, but I'm not sure. The names are hierarchical. There are two parts, a local part and a site part. The site part, this is the one where you would have multiple dots. The last part, in this case, would be the name. The site is usually authorized or managed by a central or a sequence of centralized or orchestrated managed entities, whereas the last part is usually, as said here, controlled by the local entity, the network where it resides. So, an example. In this case, the site would be mplab.bth.se and whatever is the local. .se is the top level domain in Sweden. This is managed by .se. Internet in Sweden, it's the Internet Foundational Organization. BTH, which is a domain, it's managed by BTH and SUNET, the Swedish University Network, but primarily BTH. Then we have the next domain, domain, NPLab. This is managed by me as well as BTH. There are entries in the NPLab that is managed just by BTH, and there are parts that are managed just by me. The last part, which is the host name, is completely managed by me. The traditional top domains were com, gov, edu, mil, net, org, int, and all the country abbreviations. I can't remember how many years it was, but at that point in time, ICANN enabled UTF DNS names, UTF-8 DNS names, as far as I remember. And that became, then we got a huge bunch of DNS names. So this is why we nowadays can see DNS names in non-ASCII characters. So traditionally, previously, you were only allowed to use ASCII 8, I think. And then that's changed. So now you can use whatever language you want. That is UTF-8 as far as I remember. And whatever you have in that language is translated over to a unique string that makes sense for a computer. But I would say that apart from the localized domain names, there has been a huge surplus of additional domain names in addition to the traditional ones. That doesn't really make life for a DNS server more simple. Because the job of a DNS server is to look through a list of strings and find an IP number. Or, yeah, to find an IP number. So how does resolving work? So in this case, we have our computer, we have an ISP, or someone with a DNS server. So when we need to resolve a name, what happens is that we have a local DNS resolver configured. So when IP needs to resolve, or a client needs to resolve, because IP doesn't do it, if a client needs to resolve, or a program needs to resolve a string, it sends a request to the local DNS resolver. This has a cache that lasts for between, as pointed out here. Okay, we have that one too, yeah. So, web browsers are a little bit special, I would say. Usually in a browser you might have your own small cache. But you talk to someone. Usually it's your local DNS resolver. That checks its cache. The cache has, usually I think it's a 15-minute lifetime or something. Say, I need an IP address for this string. Can you give it to me? If it has, it will resolve it and return the IP address. So then the communication is just here. In the web browser case, the principle is the same. Talks to this, checks the cache. If there's a cache hit, it responds. This guy, however, drops it down to its own cache as well, and then keeps it for between 1 and 30 minutes, just to make sure that it doesn't have to ask this again. If this entity does not have a match for the string that you're looking for, it then forwards the request to the configured DNS server that is configured, that you have configured in your system. That could be your ISP's DNS, for instance, or it could be a public DNS server. But that is the thing that it is, that it has to be specified with an IP number, not a DNS name, because otherwise you're in a loop, right? Now, if that one has it in its cache, it will draw from that and reply. This gets it, updates its local cache, and pushes it back to whoever asked for it. The next time you come around, it's going to go here, find a match, and go back. The point for this guy here is that by having a local cache, as it handles all of the requests of the customers here, the probability of it having a match in its cache is great, fairly great, as long as people are using fairly similar requests or similar sites. Okay. So, here is an example. This is the device. It has two name servers, 192.0.2.10 and 20, and those are these two devices. And then we have the internet up top on there. We have another DNS, we have two DNS servers, or two servers here. And then we have another setup over here that would handle certain other requests. Okay. So in the case that this entity asks for something that goes with that is not branch example or example, it will go up here to the internet, because this guy here can handle example and branch. In the case that if it doesn't have, if the request that you're doing is not example or branch, the request will be pushed up here to a root server, or to whatever server this has configured to use as its next server. So let's take this as the case. We're looking up for something that is called branch example. This guy asks for a.branch example. Request comes here. This checks its config, says, okay, I'm handling branch example, but actually I'm not replying to it, but this entity is replying to it. So it forwards the request to this entity. This entity can resolve a.branch.example and replies the IP number, answering. Comes here, this guy updates its cache and drops down the reply. A.branch.example is available on this IP number. This is an authoritative zone for branch example, so it is allowed to answer requests for branch example. This guy is not, but it can forward for that. In the case that we have a request that goes for example.conf, example, the request comes here. Again, this entity, I am not handling example.conf, but I know who it is, and that is this entity. Because it checks from the bottom, example.conf, branch.conf. Or so it comes up here. This is, okay, the request is for corp example, pushed over to this entity, which is now capable of replying, because it's authoritative for corp.example.conf, corp example, which pushes her back all the way down to this guy, and then down to the client. So this is an example of a recursive lookup, as far as I remember. And internet in that case. And anything that is not matching these domains would be handled by the internet. So root servers and top domains. Well, what happens if I'm trying to find a domain that is not managed by me or my organization? How do I get to google.com? Given that my local DNS server does not have a cache for google.com. So the solution is root servers. So if I don't have a match, I look at the bottom of the string, at the end of the string. What is the top domain? And in this case, for whatever mplab.se, SE is the top domain. So I will direct a request to a root server who is managing .se.
Swedish authorities.
Yeah, but how can I talk to them? Should I write a letter?
Call them.
Call them? It's been a little bit slow. But where can I find them? So I talk to the root server. The root server will tell me, you can find a DNS server for .se at this IP number. Okay? Now I direct my request for that entity. Hey, how can I reach bth.se? And I talk to the SE domain servers then. They will say, okay, BTH is found here. And then I get a DNS server at BTH. And then I send my request to BTH server, who is handling this. The BTH server will reply, yes, that is handled by this MPLab server. That's an IP number. And then I can direct my full request to that entity. Hey, who has whatever mplab.sc, bth.sc? And that will reply, that is found on IP number 192.168, 194.47, 151, something. And then I have resolved it. So, starting at the bottom and working our way up. There are 13 root servers. They're named A through M, rootservers.net. Duh, but that's a string, right? But they have hard-coded addresses. And they are, as far as I remember, hard-coded into most IP stacks, or into the programs or DNS resolvers that are around. They are using both IPv version 6 and 4, and they are distributed. Because we only have 13 name servers on the world, even though we don't look up top domains that frequently because things will be cached, we still have a lot of hosts, right? The load would be noticeable. So these are the locations for DNS servers, root DNS servers. I'm a little bit curious what these guys are. That could be, there's probably a nice small island. That would be in Indonesia, right? Somewhere. Not sure where those are. Somewhere in the middle of the ocean. So we see that we have a huge amount of DNS servers in the east coast of America, Europe, and then it's fairly evenly distributed across the world. Hey, but you just said there's just 13. Well, not quite. There are 13 root servers, but those are handled by multiple entities. And this is just so we can handle load. By the way, I think that is actually the L root server that we're seeing at these locations. They're sometimes using something that's called unicast. it's not broadcast, it's not unicast, but you send an IP packet to an address, and whatever device that is closest to handle that will reply to it. And as an ISP, you set up your network so that when you get a packet for this address, you know where is the closest root server from your network. That is why if I ping 8888, which is Google's DNS, or 8844, which is also Google's DNS, I'm not going over there. I'm going somewhere here. Same thing with 1111, which is Dutch DNS, I think, or something like that. Those are not at specific sites either. They are also distributed. So, inverse mapping. So, just like RARP maps layer 2 to layer 3, sometimes you want to map a layer 3 to a DNS name. This is difficult. Not impossible, but it's difficult. What you do is when you set up a DNS description or DNS entry, you say a.org equals this IP number. When you do that, you also set up a reverse mapping that allows you to go from the back of the IP address. You go from the IP address and then you map that to an entry. The drawback there is that you will have a lot of entries because you cannot simplify that in the same way as you do with DNS names. And it looks like this. So if this is the IP number that you have mapped, you will have another DNS entry that's called dcba.inaddress.arpa. So when you do a reverse lookup of ABCD, that is transformed into, hey, what IP number or what entry has this? This is resolvable because we walk this way, right? ARPA in address ABCD, that identifies a match, and that match is a pointer that points to the DNS name that you specified in the beginning. But you see, compared to looking up the string, this is more complicated. Secondly, there's always a high probability that the address that you have specified is used somewhere else, perhaps. If it's a public address, probability is lower. It shouldn't happen, but definitely for private addresses. Load balancing theory. How many lectures have you had in capacity analysis?
2 lectures.
2 lectures. Have you seen this yet? Okay. So I predate CMAC a little bit. This here is a very simple, or a very simple model for a queuing system. A queuing system is made up of a server, this being this entity, and a queue. A server can handle a certain amount of customers per second. In this case, mu customers per second. The queue can can hold customers that are not currently in the server being treated. The server can only handle one customer at a time. It can be really fast, handling them really quickly, but it's only one customer at a time. The queue can be 0, there could be space for no queuing, and there could be infinite space for queuing. Technically, it's difficult to do an infinite queue, but for sake of argument, we can do it. But this here is the fundamental. You have a queue, you have a server. This system, this queuing system, is being fed by customers. There are customers arriving. These customers usually, well, no, not usually, they arrive using some kind of random process. Like students dropping in through the door. There's a random process describing that. There's a distribution of the arrival intensity of students correlated to the start of the lecture, right? But for simplicity, we say that they arrive at lambda customers per second. And we have a server that serves with mu customers per second. Now, this is very simply, this is very high level. So I'm not going into details. I'm just taking what is enough for this class. But queuing is the fundamentals of telecommunications systems. In the case that we have a server that handles, put a number here, 10 customers per second. If we have customers arriving at 5 customers per second, that's not a problem. We get a customer, we treat it, and then we wait. Another customer arrives, we treat it, and we wait. And we still have enough space to do more, right? So if we have lambda less than mu, arrival rate is less than service rate, no problem. We have enough resources to serve all of our customers. In the case that we have lambda equals mu, now this is a transition part. At this point we have exactly this right amount of resources. Specifically, a customer arrives and is being served, and the moment that customer is completed, a new customer arrives, and the next one starts like this. Perfectly synchronized. The challenge with that is that it's just with a small fluctuation. Just a small fluctuation. The next customer comes a fraction of a second before it's supposed to arrive. We still have a customer in queue or being served, and the new customer then has to queue. Now, if we have a queue space, probably not an issue. But it's just on the edge. And you don't want to be there. If we're in this case, okay, now we will have a problem. We're serving 10 customers per second, but we're getting 15. Okay? Shit. So every 1 second, our queue will grow by 5 customers, right? And after another 5 seconds, we're 10 customers, 15, 20. And as long as the customers doesn't slow down, our queue will continue to build up. And if you're arriving as customer number after 10 seconds, we get 5 customers every second, right? So after 10 seconds, there will be 50 customers ahead of us, before we're being served. So that's 10 seconds before we get down to the server and being treated, right? So that will not be good, right? So how do we do that? What can we do with this? Okay. So in this case, if we're overloaded, basically. When we're having arrival rates exceeding the service rate, we are overloaded. The good thing with an overload state, or a bad thing, depending how you see it, in the overload state, you will always have a departure of a customer here every 1 by mu seconds, because that is the service time it takes. You will always have customers departing. Now, eventually, our buffer will fill up, unless we have an infinite buffer, and then we'll have infinite queuing time. What we can do here is that we can drop the customers when the queue size is exceeding a certain threshold. If we have more than 10 customers in queue, that's 2 seconds waiting time, we reject the customers. So then when the 11th customer arrives, it will be rejected. And we keep on rejecting until we have serviced one customer, made one slot available, and then the next customer that arrives will get into the queue and we'll have to wait for 9 service units. We could also be nasty and you just randomly drop a customer that is in queue and just rip them out of the queue and make room for one more. There are different arguments for these. Dropping at arrival, okay. Tough luck, you're not going to be served now. On the other hand, depending on how the protocol is done on top of you, that might be better, because then there's a problem and you need to fix it some other way. If you randomly drop a customer that is in the queue, that I think is just pure evil, because you've spent you're perhaps first in line and then you're being thrown out. But there are different ways. But we really, I'm of the argument that we should really avoid dropping customers, because eventually they are our bread and butter. They make our money. They pay for our service, hopefully. So the solution here is to increase server capacity. Yeah. So how do we do that? Well, we could increase this. We need to increase this somehow. But most likely, our system is already running at peak. We have our system, our computer. Perhaps we start by running it in a virtual machine. But then after a while we realize, okay, we're running in a virtual machine, we have the virtual machine overhead, etc., etc. We have lots of flexibility and interesting stuff from the virtual machine, but we're not getting the performance. We're getting 50 customers per second service time. We need 150. Okay? So we change this. We change perhaps to a more powerful virtual machine. We increase the CPUs and stuff. Perhaps we get a little bit higher to that. But at some point in time, we cannot increase the oomph of our engine. We cannot get more power from it. We perhaps drop down to bare metal, just running this thing, nothing else. And we cannot do anything more on it. So the solution in this case would be to use more systems. So instead of having one server, we now have 2 servers that is drawing customers from the queue. So the first customer comes here, being pushed over here. Next customer comes pushed down here, being served, and then they're pushed out. If both of them are busy, the queue fills up. The difference here is that instead of having mu customers per second, we can now do 2 mu per second. This assumes, however, that this is capable of doing this. However, that assignment process is rather simple. You can, in theory, where you can have these guys drawing the customers from the queue on their own. You just need to have a little bit of synchronization between them so they don't draw the same customer twice, because that will just be confusing. So suddenly, before in this case we had lambda customers, now we have 2 mu per customers per second. Double the performance, right? And we can actually scale this to have n customers per service by adding additional servers. Really powerful, right? Now, do you remember some of the previous lectures where I talked where you could have n something? Where you had an issue, you didn't have enough capacity, and then you could add another something, and then you get twice the capacity, and then you could add more, and you get 3 times the capacity. Link aggregation in Ethernet. It's the same thing. Now, so why do we want load balancers? Well, we have this capacity thing because what we're having here is this guy acts as a load balancer. It balances the load between the servers. So we want it for capacity reasons, or we can have it for capacity reasons. We don't have enough power in one single box. So we can have parallel boxes. We can do things we can basically get more power by using more machines. But we can also use it for resilience and redundancy. And the thing is, we use them at the same time. It's good. So in the case of resiliency, assuming this is the setup we have n servers, and we're doing our thing, we're working fine, blah, 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 blah. And then suddenly, bang, one of the servers fails. Hardware failure or something, we don't know. It just stops working. Instead of having n new servers, when we lose one of them, we lose one of the servers, and we have now n-1 new customers per server second we can handle. But we still have a capability of handling them. We lose 1 out of n. Hopefully that we have enough servers that will not be a huge problem. But we lose a little bit, but we can still service. While that is gone, we can now bring up another device, hook it up, and replace it. And then we're back to operations. From the user perspective, they are still being treated. The treatment just might be considered to be a little bit longer. But they are still treated. And as long as n times 1 mu is greater than the total, as long as n times mu, n minus 1 times mu is greater than lambda, they are still being treated and they will not perceive queuing. Now, in the case of, sometimes we hear redundancy. In the redundant case, you have scenarios, what's called cold redundancy and hot redundancy. In redundancy, the simplest, I would simplify and say, okay, we have a primary solution. This is used all the time. The moment this fails, we switch over to something else, and we use that. That is redundancy, in my point of view. While you're not using it, it sits there, it's being idle. It might be used doing something else, but from this perspective, it's not used. And it's just assumed to be ready to take over at a moment's notice. I kind of think this is better, because we're using everything as we can. We know if there is a problem, we're going to be aware of that. We're going to notice that when there is a problem, and then we can fix it. If we just made our span big enough to handle our load, we can fix this as we go. In the redundancy case, if you switch and your redundant solution fails or is not ready, you're going to have big issues, right? But they have benefits and drawbacks. Of the redundancy approach has benefits as well. That could be cheaper compared to this, because here you need to have a certain amount of equipment or resources available all the time, whereas here you just need that, and when that's failing, you activate that, and then you start paying for it, perhaps. There are a couple of naming concepts when it comes to resiliency. If you say a system is n plus x, that means that there are n servers, and the x indicates how many servers that can be disabled or failing, and the system is still able to cope. Or correction, it is still operating. It doesn't make any statement of how good it is operating. It might be that it is in overload state, but it's still operating. So examples is that n plus 1, n plus 2, or n plus 0. This is the case you do not want to be in. So, what levels can we do load balancing? I gave the first one away already. You can do it through link aggregation. Or we do link aggregation, which is kind of like load balancing. We can do it on layer 3 with routers. Where do we direct the traffic? We can also use layer 4, DNS. So, and that is something that you should not ignore. We can do load balancing on DNS. And usually DNS load balancing is geographical load balancing. So if you set up, I'm exampled on conf. I can then configure my DNS entity so that if I receive requests from Asia, I'm going to direct my IP address to my site in India. If I am receiving requests from North America or America, I'm going to direct it to my site in Denver. In Europe, I will direct the request to Frankfurt. So that's a geographical load balancing per section. And then we have the classical one on the application service perspective. You have a small proxy that receives that where the requests or the messages are coming to, and then it decides which serving entity will handle this request. This is perhaps the normal level of where you see load balancing, but remember that it's also present in the other layers as well. So here is an example of a big picture. So as I said, pointed out, here you have the requests. Initial load balancing is done by the DNS. Depending on where your request is going, it's dropped down to a pool of web servers or mail servers. These guys are then accessing SQL servers, again through a pool. And then these guys are found on a pool of database clusters. So here we have actually a quite normal load balancing scenario. You have the DNS, you have the service application, and then you have another subsequent service application behind it. All right. Any questions?
So overloading, is that leading to system failure?
Overloading could be a result of a system failure, or it could be an example of badly dimensioned system, or it could be the result of a flash crowd or something.
So when we are overload but still operating,
Yeah?
so what happened to the excess load?
Depends on how your system is configured.
Hmm.
That could be dropped. Generally, it's difficult to generalize, but I would say when you're in a low overload state, it's really unclear what happens. If you design your system properly, you design it so it will have a known behavior when it goes into overload state. If you haven't done so, you don't know what things will go through and come into your system. It could be, you don't know. If people are sending requests, some will be discarded, some will get in. You don't know. But if you design your system properly, you will have a way of controlling that. So things have improved. 10 years ago, when you went to a website and the website was overloaded, you never got a reply. And nowadays, if the website is overloaded, you usually get up a small page saying, hey, we're having technical difficulties, please try again later. You don't know what's going on there, but you get some kind of notification that there's something going on. But that could be overload or a system failure or something, but you get a notification of something. So the design has improved. More questions? No? All right. In that case, thank you, and I will see some of you guys tomorrow. Come prepared. All right, thank you.